Our next speaker is Dr. Rita Plukian from Lithuania. She is a senior researcher from the Center for Physical Sciences and Technology. It experiences nuclear physics, accelerated physics, and medical physics. Dr. Plukian.
Okay, thank you. Actually, here I am also on behalf of Radiation Protection Center from Lithuania, because I'm working in both institutions here. So, because actually I would like to talk about first results of radioxenon detection of sauna-free and free sauna cubes, which have been installed in Lithuania recently, actually in December last year. Here you can see in the map where we are located. So the cubes are located mostly on the border of Lithuania or European Union in the eastern part, let's say. So one cube is near the sea, Baltic Sea. One is near Russian-Lithuanian border, cube in Kybartai, and one is near Belarusian, on Belarusian-Lithuanian border. And the sauna-free is located in Radiation Protection Center site in Vilnius, in capital of Lithuania. And actually, it was this network was made to detect the radioxenons, which could be released, let's say, from nuclear power plant nearby in the neighboring country, in Belarus. And in the picture, you can see the photo taken from the hot air balloon from Vilnius. So it is nearby, and it's something like 50 kilometers from Vilnius. So in emergency case, it should be evacuated and things like this. So we are worrying very much about what could happen and install it with network. It's national network, actually. But of course, we can detect the other events over the world from different reactors. So here you can see what installation we have. It is all the parameters taken from Anders' publication here, but you can see the main performance parameters and also minimal detection concentration of different systems what we have, the cube and the sauna-free in comparison with, for example, sauna-2. And here I borrowed this map from the CTBTO site and erased actually all the not working reactors and put the working ones. And I put also Lithuanian network, which is in the marked in red here, and all the in the right corner, you can see all the installations around Lithuania, which could be the possible sources. And also in the tables, you can see the distance from Vilnius, let's say. So the main nuclear power plants and medical isotope production facilities as well. So here's the summary of the data what we have so far. It's from different cubes stations and sauna-free. So you can see what the maximal values of radioxenon 133 is about 20. And it depends also on the date. Sometimes it is, sometimes not, but mainly. And also, two isotopes we are detecting mostly. It is 133 and 131 metastable. So here maybe I will show the results of the actual data what we have. So at the beginning, from the cube 17 on the Belarusian border, it is operating almost a year already. So, and other installations have been installed. It is almost 9 months of operation now. So actually, we have not too much, but with high value, we have something like 9 significant events. And in red, you can see which has more than one isotope detected. So usually we are doing modeling, backward modeling with high split if it is more than 5 millibecquerels per cubic meter detected of 133 activity concentration. or if several isotopes are detected, like here. Here you can see with similar data, but for 131 metastable. And I forgot to say, but it is our guess above the date when it was measured. The higher value, it is our guess with high split. But of course, I will show later more explicit view. 2 times we have detected xenon 133 metastable. One was in the cube on the Baltic Sea border, on the Baltic Sea, and one in Vilnius, recently actually, in July 18. And there was no actually detections of xenon 135. But we had one event when activity was not activity concentration, but activity was detected also in July 18. So what we are doing usually, we have always Argos modeling of atmosphere transfer. And if we have some detection in xenons, we also measure, we are doing high split modeling. So here I wanted to show also, because you can see the poster number of PNL measurements. So PNL station is also in Lithuania longer already. And it was one detection in last year, December 5th, then they detected, and our one cube haven't. So it was interesting from the point of view that more installations you have, better results, of course, you can get. And here I will go quickly, just as I said, we are doing high split backward trajectory modeling and backward dispersion modeling, and we are guessing which would be most possible source from where the atmosphere transfer could be detected with xenons. So it is in different, as I said, up to the end of the year, it was only one cube, so mostly the results are from this data. So usually we have lots of detection from Russia, but also we have from the western part, from Fleurus, from Belgium, some detections in different cubes here, when already all network was ready. And here is, as I said, the last hour detection with few, with all 4 actually radioxenons isotopes. So our guess was that it is Belarusian nuclear power plant, because in several stations it have been detected. But of course, now we are working on implementation of PSRs and FRIERS methods for source attribution and analysis. And more, it is it was already in the poster today, but you can also find information. And also, other thing I was actually inspired was inspired by Dr. Kalinowski. He was talking about the isotopes ratio. So we also we are trying to do some modeling of different reactors using scale and MCMP codes, and to get the generation of xenons isotopes at the different reactors. So we did different modeling, and we were trying to get different isotopes ratio at different reactors here. Of course, it depends on the power, on fuel enrichment, on burnup, but we guess but it could be possible, the composition like this and the xenon ratio like this. Of course, all 4 isotopes are required to identify the source, and it is necessary to know the reactor operating parameters and the transfer time. So what we did, as we were concerned a lot of Belarusian nuclear power plant in Astravas, which is quite close to our border, So we established the two scenarios, let's say, from VVR type reactor, slow scenario and fast scenario, with different wind speed, just very simple, direct atmosphere transfer. And we think that in Vilnius, the fast could be in 0.3 days, and slow, for example, scenario, xenons could be transferred to 1.4 days, let's say. And whereas you can see in the table for the different cubes. And model estimate of possible xenon ratios at a O2.3 station from nuclear power plants with different type of reactors in slow wind speed, let's say. The xenons ratio could be like presented in the table. And you can see that, for example, with slow wind, at O2.3, Vilnius and Kybartai, the closest to the border stations, only from Belarusian nuclear plant, xenon 135 could be detected. But if the wind speed is higher, of course we can detect radio xenon 135 also from different reactors as well. And here I put possible detections on theoretical detections, let's say in the graph, for different wind speed and for different reactors, what we can expect. And I put also one radioxenons ratio, which we have detected in our network, let's say, in Vilnius actually. And I expected what it should be between red points, if you can see in the magnified view, but it is not, so probably mixture of different xenon emissions, it could happen here. So conclusions are that the sauna-free and cube station system has been installed in Lithuania, allowing for the recording of xenon emissions from the Belarusian nuclear power plant and other nuclear facilities. The xenon station results will contribute to efforts to ensure the safety of the population of Lithuania in event of nuclear accident. And during the measurement period, the most frequently measured are two isotopes, which were detected above the minimum detection concentration limit. However, there are no significant emissions and no risk for the human health. And by analyzing measurement data combined from several sauna stations and using atmospheric transport model, so with actual and or predicted meteorological data, it is possible to identify radioxenons emissions sources with better precision. Okay, thank you for your attention, and if you have any questions.
Thank you, Dr. Pulkien. We have time for maybe one or two questions.
Thank you for your very interesting talk. I just had one quick question. I was just wondering what resolution the meteorology you used with high split was.
Actually, my colleague is doing high split modeling, so you can see in the poster with more details, because I'm just more data, you know.
Thank you.
One more question, Dr. Klinowski.
Yeah, very interesting presentation, Rita. Of course, all your observations in the atmosphere are of interest in identifying sources. I find it interesting that you do modeling on the isotope composition of the different reactors. And then you quote numbers in the table. Are these for the equilibrium situation of the reactor? Because within the reactor, even the isotopic ratios change during the course of operation when the power is ramped up and down. And then when the xenon is released, It depends on how the abatement system in the reactor
Yeah, of course.
treats them. So I just saw it from my presentation that the ratios change over time. So
Yes.
how can you hope to distinguish between different reactor types at a distance?
It was just, preliminary modeling just to have an idea where it could be, but of course, you are right, we need to have better scenarios, what accident could be, how long time it would take to decay in the reactor itself or in the covering of a reactor, or how fast it will come out from the reactor and things like this. So this was not modeled yet. So
Maybe I can follow up. Is that okay? The most interesting for treaty monitoring is whether the isotopic ratios cross what we call the threshold for screening. For example, xenon 135 or 133, when is it more than 5? So maybe you want to focus your investigation into these special situations of isotopic ratios.
Okay, with that, let's thank our speaker.
Okay.
Thank you. Move to the